Howdy, welcome to Calculus with Isaac. I am thrilled to start a new series on Ordinary Differential Equations, or ODE. I highly encourage subscribing to the channel to follow along and stay updated. An ordinary differential equation, or ODE, is a mathematical equation that relates a function with its derivative. In simple terms, it's an equation that describes how a quantity changes over time or with respect to another variable. For example, Newton's law of cooling can be expressed as a first-order ODE. This will be discussed later on in this video. Here, X is the temperature difference between an object and its surrounding, and T, of course, is time. ODEs can be classified based on their order and linearity. Let's first cover order of an ODE. The order of an ODE is determined by the highest degree in the equation. First order ODEs contain only first derivatives, like the cooling example that we saw earlier. Second order ODEs include second derivatives. Here is an example. Third or high order ODEs contain derivatives of third order or higher. And here is an example of such ODE. As mentioned earlier, ODEs can also be classified as linear or nonlinear. Let's first define what linear ODEs mean. A linear ODE is one where the dependent variable and its derivative appear only to the first power and are not multiplied together. Here is an example of a linear ordinary differential equation. To be more precise, the above ODE is a linear second order ODE. Due to 1, the highest derivative is of second order. 2, y and its derivatives appear only to the first power. Lastly, there are no products of y or its derivatives. And on the other hand, nonlinear ODEs are expressed in different form. Here is an example. This is a nonlinear first order ODE. 1, it contains y squared, which is y multiplied by itself, of course. 2, it contains the sine of y, where y is inside a trig function. One thing that I would like you to take out of this video is the distinction between linear and nonlinear ODEs. This is important because linear ODEs generally have a well-established solution methods, while a nonlinear ODEs often require more advanced and complicated numerical methods to use or techniques. Just for fun, let's do hands-on math. I claim that x is equal to cosine of t plus sine of t plus c multiply e raised to negative t is the solution for the Newton's law of cooling example that we saw earlier, where c is an arbitrary constant, of course. This means there are infinitely many solutions, each corresponding to a different value of c. Don't take my word for it. Pause the video and try to verify this. Okay, let's work through it together by plugging in the claimed solution back into the Newton's law of cooling ODE, which was dx over dt plus x is equal to 2 cosine of t. Since we know that x is equal to cosine of t plus sine of t plus c times e raised to negative t, we just need to find d of x over dt by taking the first derivative of x. dx over dt is equal to negative sine of t plus cosine of t minus c times e raised to negative t. Now it's a matter of plugging it in. Once we plug in, we have negative sine of t plus cosine of t minus c times e raised to negative t plus cosine of t plus sine of t plus c times e raised to negative t. We can cancel out the signs because we have positive and negative, and you can cancel out also the e's, and we are left with 2 cosine of t. Thus, the claimed solution satisfies the equation for any value of c. In the next video, we will discuss some real-life application of ODEs and discuss what you need to know to study them effectively. Stay tuned.